Number 1 asks us for each graph below, use function notation. So that's like f of x, like this, to describe the transformation of f of x that would better fit the data. And the data in this case is the dotted lines. So I'm just going to write down just this f of x outline here, and then we'll fill in information as we go. And I'm leaving a little bit of space inside the parenthesis in case we need to add in any numbers. So I like to look for a point that's easy to notice where it goes, like a min or a max. So I look at this point and I see that it moves directly to here. And so you can just kind of count how far over that moves. So this one started at -2 about and went to 0. So this is moving 2 to the right. And when we do something on the inside of the function, it always ends up kind of opposite of what we think. So it's moving 2 to the right. And so it's going to say just -2 on the inside of our function. So anything inside of these parentheses impacts the left-right movement of the graph. So then this will be f of x -2 to move it to the right. Now B kind of does two things. So we see that it is flipped over and this point is moved up. So I'm going to talk about what happens from this point. So we're going to do a reflection, right? So that it ends up like this, so that our graph is the same position as this one. And so that was a reflection, and I flipped it over the x-axis. So I flipped the graph up and down, right? So I flipped this V to be downward. And so that is impacting the Y values, or the vertical movement of your function. So that's going to be a negative outside. So a negative impacts or does a reflection. So a negative outside reflects it up and down. A negative inside would flip it left and right. Then after there was a reflection, then this point moved up however many units that is. So up 1, 2, 3, 4. So up 4 units that it landed directly on those dots, right? So now it moved up 4 units, and anytime you have up and down movement, that's on the outside of the function and exactly what it seems like. So this one, and let me just clean it up so that we don't have all that space. We just have negative f of x and then a +4 on the outside. So this negative flips it up and down, and then this +4 moved it up 4. Then in part C, so again, I would pick some point that's easy to see where it moves to. So this point here is going to move here. And so it looks like it's moving in a diagonal, right? So we're going to break it down to how far did it move to the left, and then how far did it move up. So we're going to count that. And the left-right movement, so that's 1, 2, 3, 4 units to the left. So that's going to end up being a +4, so kind of opposite what it feels like on the inside. And then this up and down movement, okay, moves 1, 2, 3 units up. And that's going to be on the outside of our function, exactly what it feels like. So f of x +4 and then +3. Number 2, using each sequence of transformations, write them in function notation as a transformation of f of x. So this one says a translation 3 units right. So that's going to be inside, and then 5 units up. So we've got this f of x, right? And then we've got 3 units right. Okay, so move to the right. So that's going to be a -3, opposite of what it feels like. And then 5 units up is on the outside, so +5 on the outside. Next one is a translation of 6 units down. So 6 units down is on the outside, so that's just going to be a -6. So that's just going to be f of x -6. And then a reflection over the x-axis. And so the x-axis means that we're going to be flipping it up and down, right? So we're going to be reflecting it over that. So that's a vertical flip. okay, or a flip up and down, which would mean that our negative is going to be outside of our f of x. Then we again have a reflection over the x-axis and a translation 7 units to the right. Okay, and that right movement is going to be inside of our function. Okay, so 7 units to the right is inside, and to the right is this way. So it's going to be a -7 when it's on the inside. And then the reflection over the x-axis again is a negative outside of the function. Number 3, in the following images, f of x is the solid line and g of x is the dotted line. Sketch a graph of h of x. So in part A, it's saying that we're going to do f of x plus g of x. So we're just going to be adding these two together. And so you can do a couple of things. So f of x is like the output of this. So thinking about the y value, and g of x is the y value of this green one. So here at x equals -4, this one's at 0 and this one's at like 15, a little bit above 0 and then at 15. So if we add those, the new addition is going to be just above 15. Or here, a little above 0 plus 15, again, is going to be a little bit above 15. This one's maybe at like 3 plus 15 is like 18. And so it's basically going to do this same black line, just moved up 15 units. Okay, so like if we go to here, this one's at 10. So at this x value, it's at 10 plus 15. So 10 plus 15 is 25. It's going to be here. Okay, or here, they're both at 15. And 15 plus 15 is 30. So you can kind of see this line happening. But it's just going to basically move this black line up 15 units for that one. Part B, so now again, f of x plus g of x. So here, our g of x is at 0. So 0 plus this will stay at this spot, right? So they're going to connect there. Okay, and then over here, we're at negative something plus this number. So it's going to be a little bit lower, because if this is like -5 plus 62, that's like 57. So it's going to be below the black line here until here where they meet. Okay, now here you're at this x value, you're maybe at like 5, and here you're at 8. Well, 5 plus 8 is like 13. So it's a little bit higher than this. Okay, this is like 1 plus 9, so that's maybe going to be 10. 0 plus 10 is 10. This one's maybe at 8 plus 15 is 23, but above, right? Because these are both adding together two positive numbers, so it's going to be higher than each of them. So here you were below until you hit here, and now you're above both lines as you're adding them together. Part C, we're going to subtract them. So we're going to do f of x, which remember is the solid line, minus g of x, which is the dotted line. And so we're going to do 0 minus 15 would give us like -15. A little bit more than 0 minus 15 is a little bit higher than 15. So we're basically just going to move this black curve down 15 units because we're subtracting the same number off of it every time since this green line stays the same. And so if you wanted to plot a couple of those, here's where they're both 15. So that's going to be at 0 when we do 15 minus 15. Here we're at like 18 minus 15. Like 8 minus 15. So like -5. But so it's just going to be that curve just below. Move down by 15. All right, and then here we're going to subtract again. So the f of x is the solid, the g of x is the dotted. And so when we subtract a negative number, right, that's actually going to get bigger. So here, let's look at where this one is at 0. So when we do 28 minus 0, that's going to be the same number. Now for over here, this will be like 40 minus -1, which would be 41. So it's going to be above that this time. Or this one's going to be like 62 minus -5. So that's going to be like 67. So over here, when the green is less than 0, then we're going to be above the black line. So here, if we did 20 minus 2, that's like 18. Now we're going to be below it. Or here, they're the same, so we're going to be at 0. Here, it's going to be 0 minus 10, so we'll be at negative 10. Okay, and then again, here's where they're the same. So like 18 minus 18, that's going to be 0. Here we can kind of see this one's maybe 28 minus 20. That's going to be at 8, but it's going to stay below this because this black line, we're going to be subtracting a number. So it's going to be getting smaller. So here it was above the black. They connected. We knew where it was at 0, below 0. Okay, and now it's not going to go above that black again. Number 4, functions f and g represent the temperature, f of x and g of x in 2 apartments, x hours after midnight. Describe these functions in context. So for this one, remember f of x and g of x are the temperatures. So here the temperatures are the same in both apartments because it says f of x equals g of x. So after midnight or whatever, the temperatures are the same. Then in the next one, we have that f of x equals g of x plus 3. So the temperatures, the temperature in f is the same, or let's say at midnight. So the temperature at midnight in apartment F is the same as the temperature in apartment G at 3 a.m. since this says X plus 3. So if we said midnight, this would be midnight plus 3 hours. So that's just one example. Midnight, it would be the same as 3 a.m. You could even say, at 1 a.m. in F, it's the same as 4 a.m. in G. So you could change this, but there's just a 3-hour difference. Next one says that the f of x is greater than g of x. So the temperature in apartment F is higher than the temp in apartment G. And then the final one here says that f of x equals 1.05 times g of x. So the temp in apartment F is 1.05 times higher than the temp in G. So if you knew it was 70 degrees in G, you could just do 70 times 1.05, and that would tell you how much it was in F. All right, number 5, the function A gives the height above ground of a point on a Ferris wheel. The function B gives the height of a different point on a different Ferris wheel and is defined by B of S in the function, in these functions below. So in the functions, S is the time in seconds since the Ferris wheels started moving. So for B of S below, describe how the Ferris wheel modeled by B compares to the Ferris wheel modeled by S. So in this first one, it says that B of S equals 3 times A of 0.5 S. So this 3 on the outside means that B is 3 times higher than or taller than A. And then that 0.5 on the inside then talks about its speed. So and is half the speed of A. Then in part B, we have that B is half as tall because the outside impacts the height. So it's half as tall. And then the 4 on the inside talks about its speed. So, and it is 4 times faster than A. So it's half the height, because remember the outside impacts the height, and then the inside was talking about the speed, so then it's 4 times faster. Then part C, we get that B is starts 40 feet higher. So it's not times taller, since this is 1/2 times or 3 times. This says plus 40. So B starts 40 feet higher, or whatever the height is being measured in, and it doesn't gives the height above ground. It doesn't really say in here. So I'll just say feet. So B starts 40 feet higher than A and travels 1/4 of the speed, since the 0.25, so 1/4 of the speed. Or you could say 4 times slower, or 1/4 of the speed. All right, in number 6, we're looking at deciding if functions are even, odd, or neither, and explaining how we know. So in A, B, and C, it's on a graph. D, E, and F, it's in from an equation. So when we're looking at a graph, if it's even, there's going to be it's going to be reflection symmetry over the y-axis. Okay, so symmetry over y-axis. And then if it's odd, then it needs to reflect over both. So there needs to be symmetry over both, kind of, but just reflect over x and y axis and land on itself. So let's take a look at part A. So if it's able to flip over the y-axis and land on itself, then it's considered to be even. So this one is even, and I'll show you that if we just flip it left or right, it'll just land back on itself. So that means that it has symmetry over the y-axis. So then this one is even. Next one, if I just kind of draw in these points just so we have a visual, then let's take a look at reflecting. So let's flip it over the y-axis, and then let's flip it over the x-axis, which would be up and down, lands back on itself after reflecting over both. So that means that this one is odd symmetry. And then let's look at this last one. So if we take this and we flip it left, right, which would be over the y-axis, and then we flip it up, down, which would be over the x, it does land on itself. My drawing's a little bit off, but so does land on itself. So then this one is odd since it flipped over both. Now, when you're looking in an equation, even and odd becomes a little bit different. So I'm just going to write it down in the corner here. So if f of x equals f of negative x, then it's even. So when you plug in, what we're going to do is we're going to plug in a negative x. And if we get the exact same function back, then it's even. So equal, even. If we plug in a negative x and it gives us back the opposite of our function, so everything is exactly the opposite when we plug in a negative x, then we're going to be odd. So opposite, odd, equal, even. So let's go ahead up here and look at just plugging in that negative x. So you plug in the opposite of x into your function. So wherever you see x, you're putting in a negative x. And then just simplifying. So we're putting a negative x here. Well, negative x squared, negative x times negative x is positive. So we get x squared and then plus 4. And that's our f of negative x. That's also exactly the same. This is exactly the same as f of x. So that means that f of negative x is equal to our original function, f of x. So that means that this is an even function. So we'll do that again over here. So we're going to plug in negative x everywhere we see an x. So we have f of negative x, plug it in here. And negative x cubed is going to be negative x times negative x, which is positive x, times negative x again, which gives us negative x cubed. And then we have minus 2. And so remember that. So here's our f of negative x. And now if we take and do the opposite of this, because it's not equal to this, but if I just went and did the opposite of this, this would be negative x cubed, and the opposite of negative 2 would be positive 2. So this doesn't equal our original function, and it doesn't equal the opposite of our original function either because of this. So this is not part of the opposite. So this is neither even or odd. It's not equal and it's not opposite. All right, then our last one here, we'll plug in that negative x again and see what happens. So we're going to plug in negative x. So our f of negative x is equal to, so negative x cubed, again, is negative x cubed. And then 8 times negative x is negative 8x. So this is not equal to our original function because we've got negative versus positive, negative versus positive. But if we do the opposite of this, the opposite of x cubed is negative x cubed. The opposite of positive 8x is negative 8x. This is the same as this. So f of negative x is equal to the opposite of our original function. So this means that this is odd, that f of x is odd. All right, number 7, given the two graphs below of two objects that have been dropped from the top of a building, let's do a couple of things with this. So let's name a couple similarities and differences. So here are our two graphs. So what are some similarities? What are some differences? So both graphs are starting at the same initial height, which is 50. So you can see that here. They both start at 50. And they are traveling a similar path. So it looks like, you know, they're descending in a similar fashion. Like one isn't just going diagonally straight down. They've got a little bit of a curve down. But then some differences. But the second graph is falling at a slower speed since it takes longer to hit the ground. So we can see where they hit the ground. This first graph hits the ground after 10 seconds. The second graph hits the ground after 14 seconds. So what does 0, 50 represent in this context? So here's 0, 50 in each one, and that would be the initial height. Or where how high they're being dropped from, right? So they're being dropped from the top of a building. So 50 feet is how tall the building is. And then what is 10, 0, and 14.1420 represent? And this is the time it takes each object to hit the ground. So the first object, like we said, took 10 seconds, and the second one took just over 14 seconds. Then let's sketch the difference of these two graphs, okay? So remember, difference means subtracting, okay? So difference means subtracting. So we want to subtract these. So if we do, they're at the same spot here, 50 minus 50, that's going to be 0, okay? And if we subtract here, they're very small, right? The difference is you can't even see the difference between the two graphs. So that's going to be really small again. And if we go to here, the difference, and you can see the difference because the difference is how far apart they are. So the difference is this wide. So then that's going to be how far the difference is. And it just keeps getting wider, right? The difference keeps getting wider. So the where you plot your dot. So I'm trying to make my dot be about this far from the x-axis right here, right? Because that's how wide it is. So here the width is at 0, so it's going to be on this curve. And so then it's just going to, you'll just get that curve, and it should go through that dot. I just missed it when I was drawing it. But the difference is how far apart they are.